as engineers, we're often going to consider test data, whether that's from some sort of experiment or whether it's just some production data or something. We're going to have to draw conclusions based on data. The most basic scientific function, if you think back to like third grade when you learned about the scientific method, the general process for the scientific method was I'm going to form a hypothesis, I'm going to test that hypothesis with an experiment, and if the experiment shows me one way or the other with respect to the hypothesis, then that's the conclusion that I draw. And a good scientist will allow the data to guide the discussion and not have, bias and other things that affect the conclusion that they draw based on a certain hypothesis. But that's the basic scientific method. We need to figure out what our hypothesis is that we want to test, whether that might be, are my production rates higher on Tuesday than they are on Thursday? Is there a difference in ultimate tensile strength between heat treatment A and heat treatment B on this material? Many, many different things that we can test, many different hypotheses. We're going to talk a little bit about the most basic and most common ones in this and a couple of other subsequent videos. But the question is, why do we need a process? Why can't I just look at the data and draw a conclusion? We have this kind of built-in need or a tendency to use just quick heuristics and boom, I've solved it. I can look at the data and say this is clearly this, or it kind of looks like this is what's going on, so I'm going to assume that's the case. Because we are engineers, we have to be deliberate about the process that we use. We need to be objective whenever we can. We need to remove subjectivity such that the conclusions that we're drawing are not a function of our own biases, but that other people who would conduct the same experiment would reach the same conclusions. That's the core, the key component of doing science well, is that we remove the human aspect so we can draw real conclusions about what's going on. As a result, we need some sort of objective process that allows us to draw consistent conclusions with what the data shows. Let's look at an example. Ohio as a state has a pretty diverse population. If we split it along the I-71 corridor, there's a lot of difference between the physical geography, things like hills versus flatland, the type of soil glaciated versus unglaciated, and human geography, the type of people and cultures that you find on one side of 71 versus the other. So, are there differences, are there physical differences between people who are born and raised in the eastern half of the state and the western half of the state? Let's form a hypothesis. Let's hypothesize that there is a difference in human height between people who are born and raised in the eastern half of the state and the western half of the state. How would I test that hypothesis, as simple as it seems? Well, one might assume, well, go get some samples of data, right? And I'm going to go get some samples and test them. So let's say we get 5 samples from each half. And the 5 samples from the west are over here, the 5 samples from the east are over here. When I formed my hypothesis, my very basic and not very well thought out hypothesis, is there a difference in height? I can see that, well, oh yeah, there's variation in this variable. As I measure it, there's variation in height from one person to the next. And if I took a different set of data, as we'll see in just a second, it might reflect something different from the same populations. So let's say I took 5 measurements from the west, 5 measurements from the east. It's hard to tell whether there's really a difference in average. The average looks like it's about the same. Maybe a slight upward shift, but it's kind of hard to tell. The variation looks about the same as well. And so as a result, these two sets of random samples look very much like they could have both come from the same population. In other words, this kind of reflects the idea that maybe there is no difference, but I can't tell definitively that there is no difference. I can't say that there is no difference because there's random variation here. But I can't say that there is a clear difference. I certainly can't make that statement. This is the difference between proving the null hypothesis, that there is no difference. I can't do that. And rejecting the null. We only can reject a null hypothesis if there's a significant enough difference between the two data sets. If there was a huge difference in height, but still we would need some process of getting there. So let's say I take this sample. I don't really see much here. Based on this sample, I don't see a statistically significant difference. And if we did the math behind that, that's for another video, it would probably bear out that there is no statistically significant difference in between human height, whether that's average human height, where I would be comparing the means, or the variance in human height, where I'd be comparing the variances from the western half of the state to the eastern. Let's say I take another sample. I take another sample and I get a similar amount of variation here, but now we see, wow, this sample is actually pretty tight. It has low amounts of variation and clearly has a very different average. And if I did a statistical test here, it may reflect that there is a significant difference between the western half of the state and the eastern half. So the question remains, what process do I need to use in order to make these determinations? Well, the first thing we need to do is think a little bit about the statistics. The question that we're going to ask in earnest is, what is the probability that sample A, the western half of the state, and sample B, the eastern half of the state, came from the same population? In other words, what is the probability that these two sets of 5 measurements could have come from the same population where there is no difference? And if that probability is really high, then the leftover probability, which is the probability that they did not come from the same population, would be very low. And therefore, I wouldn't be able to reject this notion that there's possibility that there's really no difference between the two data sets. So we're going to consistently test this kind of hypothesis. This is called a null hypothesis. It says, what is the probability that these came from the same population? Because that's actually not terribly difficult to calculate. And if that probability is extremely low, then the 1 minus that probability, the opposite probability, is that they didn't come from that population. They didn't come from the same population. If the probability is very high of that, then I can state that with some level, some calculated level of statistical significance. I can tell you the chance or the probability that that is the case. I can never say anything, really statistically speaking, with 100% certainty, but I can do it with 99% certainty or 95% certainty, sometimes even better than that. And in those cases, we can draw meaningful conclusions that have a certain level of confidence associated with them that, again, removes us from that process. So in other words, the question we're going to ask is, what is the probability that there is no actual difference between the group sample A was drawn from and the group sample B was drawn from? As you've probably seen in the statistics class, this is called the null hypothesis. I can't prove the null, but I can reject it at a certain level of statistical probability. So if we look at the process that we have here, we have to first ask the question, what do we want to test? Remember, with this data, there's variation and there's an average, and the two groups have their own variation and their own average. So we have to determine what a variable of interest is. Usually what we're going to be doing as engineers is testing either the mean, the variance, or both. There are some probability tests where we need to do kind of binomial distributions. What's a probability that this happens and not this, kind of more characteristic distributions, that type of thing. But the vast majority of the work that we're going to do as engineers is numerical in nature and comparing numbers. So the two that we're going to focus on generally in this class, and you probably focused on in your statistics class, were tests for the mean, which usually include the t-test, and test for changes in variance, which is an f-test, or a change that reflects kind of both, where we'll look at something like an ANOVA, or an analysis of variance. So we need to figure out what is my variable of interest and reflect that in our question. The original question that we asked was, is there a difference in human height between people from Eastern Ohio and people from Western Ohio? That question is not specific enough for us to draw any conclusion. The question, for example, is there a difference in average human height between Eastern and Western Ohio? Now I can compare that. Or is there a difference in the variation in height between people from Eastern Ohio and Western Ohio? That's another thing that I could test, and it's a different test. So we need to have certain levels of specificity in the questions that we ask. That should be reflected by our need for the information and what's important. What is more important, the variability in some variable of interest, or is it the average value? Is it the maximum value or the minimum value? What is it? And you need to identify that and then derive your experimental method based on that. So Here's the basic process we're going to follow whenever we do a hypothesis test. First, we're going to formulate hypotheses. We need two. We need one called the null hypothesis, like we said, that reflects that there is no statistically significant difference between the variable interest of sample A and that of sample B. Then we also need to form an alternative hypothesis that's very specific to determine how we run the hypothesis test, which mathematical approximation we use. The alternative hypothesis states that there is a statistically significant difference between the variable of interest in sample A and sample B, whether that is simply a not equal to, whether that is greater than by this threshold, or is simply just different than. All of these cause different types of tests or different math in the test. The second thing we need to do, once we form our null and alternative hypotheses, the thing that we're comparing, the variable of interest that we're comparing, will help us determine the relevant test statistic. In the case of a t-test, we're going to calculate a t-value. In the case of an f-test, we're going to calculate an f-value. These are called the test statistics. Then we're going to find the critical value of that test statistic and compare it to the calculated value from our experimental samples. So we're going to say, well, I'm going to run a t-test because I want to compare average heights. And if I run that t-test, then I need to determine, okay, I want to know whether there's a statistically significant difference at, say, the 5% level of significance. What that means is I want to be 95% certain that I am basically correctly rejecting the null hypothesis. So what I need to do is find the t-value that tells me that I should reject the null at 5% probability of being incorrect, and compare my test statistic, my t0 calculated value, and compare the two. And if my difference is greater than that is needed to establish statistical significance, then okay, I can draw that conclusion. If not, then not. So you formulate your hypotheses, you determine the relevant test statistic to test that hypothesis, and then you look up the critical value, whether that's in tables or using Excel, and determine whether or not your data from your samples reflects the change that you're looking at. That's it.